Hi, this talk is Perception of Concatenative versus Neural Text-to-Speech, Differences in Intelligibility and Noise and Language Attitudes by myself, Michelle Cohn, and Georgia Zellou. People are interacting now with text-to-speech or TTS voices in their everyday lives, such as with Siri, Alexa, and Google Assistant, and there are efforts to make these TTS voices as human-like as possible. One method is concatenation, or concatenative TTS, where individually recorded utterances by a voice actor are chunked into segments and then recombined by unit selection, giving us the original Alexa and Siri voices. A newer method is via neural TTS, which is rapidly being adopted industry-wide. And neural TTS generates fully synthetic speech based on all the previous utterances in a speaker's dataset. And autoregressive methods, such as long short-term neural networks, for example, incorporate the immediately preceding context for each word production as well, overall resulting in more naturalistic output. So for example, we can see here the mean opinion scores for WaveNet in blue, a neural TTS model, relative to concatenative TTS in peach, and can see that it's closer to the ratings for real human voices shown in green. So we ask, do different TTS methods differentially impact intelligibility, and to what extent are they akin to different speech styles seen in human-human interaction? So here we can kind of think of concatenative TTS as more similar to clear speech, where each segment is realized and combined in a canonical, kind of less context-dependent form. On the other hand, neural TTS could be considered more casual speech, where words are conditioned on the local acoustic phonetic context, may be more likely to have greater co-articulation or segmental overlap in their articulation, as well as phonetic reductions such as fillers like or . Okay, so our first question is, are there differences in intelligibility across the concatenative and neural TTS types? One prediction is that the more clear speech, here concatenative, may have better intelligibility and noise versus casual. So this would be in line with the clear as concatenative and neural as more casual speech. On the other hand, there's some evidence that greater segmental connectedness, or that co-articulation, in natural speech and in TTS speech might aid listeners in identifying a signal. So here, on the other hand, we might predict higher accuracy for speech and noise for neural than concatenative speech. So for example, Hawkins and Slater in 1994 presented listeners with synthetic TTS voices varying in degree of vowel to consonant co-articulation, and found that in a speech and noise task, accuracy was higher with that co-articulation. Okay, so in experiment 1, we test these predictions by examining listeners' keyword identification of accuracy in sentences presented in noise for the two TTS types. So our participants consisted of 28 American English speakers, all of whom were undergraduates at UC Davis. And the stimuli consisted of 192 spin sentences, or speech and noise perception sentences, that are widely used in other speech and noise perception tasks. 96 high semantic predictability and 96 low semantic predictability. So for example, the boat sailed along the coast, the keywords at the end, versus Miss Brown might consider the coast, less predictable. And all of these sentences were generated with both neural and concatenative TTS with the same speaker's data set. So we're holding a speaker constant. We could imagine that some speakers may be more intelligible than others. So we really want to hold that constant and see if just this TTS method manipulates intelligibility. So we used 4 AWS poly voices, all of which were US English female voices listed here. So we can hear some examples. And so here is one in the concatenative TTS.
The boy might consider the trap.
And then the same sentence, same speaker, produced in neural TTS.
The boy might consider the trap.
So we took all of those sentences and mixed them with speech shape noise at 2 signal to noise ratios, so -3 and -6 decibels. On each trial, participants heard a sentence produced in one of the TTS types, neural or concatenative, and their task was simply to type the last word of the sentence. So here, the boat sailed along the coast, that keyword would be coast. All right, so each subject heard all 192 spin sentences just one time. And for each subject, the sentences were randomly assigned to a speaker, so one of those 4 AWS poly voices, TTS condition, and noise condition. And we coded accuracy binomially, so 1 if they got the trial correct, 0 if not, and analyzed it with a mixed effects logistic regression with the main effects of TTS condition, neural versus concatenative, signal to noise ratio, -3 decibels versus -6, and predictability, that high versus low, and all of their interactions. All right, so let's go through those one by one. So first, we found an effect of predictability, where participants were able to identify the keyword in high predictability sentences better than low predictability. That's a good sanity check. We can see that here. So we have high predictability in the left panel, low predictability in the right. We can see it's a lot higher. All right, so for signal to noise ratio, we also found a main effect where the -3 decibel signal to noise ratio sentences were identified more accurately than those at the more difficult listening scenario. We also found an effect of TTS condition, where overall accuracy was higher for concatenative versus the neural TTS. So here, concatenative is in green. We can see it's higher in both panels, whereas neural is lower in blue. We also found one interaction between signal to noise ratio and predictability. So even lower accuracy at the low signal to noise ratio and low predictability. Okay, so an interim discussion. So here we found evidence that the concatenative or clear productions were more intelligible than the neural or casual productions. And this is really in line with prior work in human-human interaction, showing a benefit for clear speech relative to casual speech and noise. And contra those co-articulation accounts that would predict that greater co-articulation would lead to improved speech and noise perception. So now on to experiment 2. So here we asked whether there was variation in intelligibility for neural TTS and concatenative DTS uh, based on an individual's language attitudes. So here's that mean opinion score again, but that's average. So we can imagine that there may be patterns of variation in how human-like or how natural a given user finds the voice, and we ask whether that could impact intelligibility. So the same set of participants as in the first experiment completed the second experiment after the speech and noise task. So they heard one sentence by each of the 4 speakers in the 2 TTS conditions and rated the voice using a sliding scale from 0 to 100 on 4 dimensions. So how machine-like to human-like being 100, machine-like being 0, how familiar, how natural, and how likable. So we analyzed these ratings in separate linear mixed effects models, the main effect of TTS condition, and by listener and by speaker random intercepts. And for all of them, as we can see in the plot on the right, there was a significant difference between the TTS types. So higher ratings for neural versus concatenative. So we see that for human-like, likable, natural, and a smaller but moderate effect for familiarity. So our second question is whether a listener's rating of a given voice is related to how well they can hear that voice in noise. So here we again modeled original accuracy in that speech and noise perception task with the fixed effect of TTS condition by rating score, so familiarity, likability, and so on, in separate logistic regression models. And we found a significant interaction between rating and TTS type for 2 ratings. So accuracy is higher for neural TTS voices when they were rated as being more human-like or more natural, with no effect of familiarity or likability. So overall, we find evidence that intelligibility differs for 2 different TTS methods, concatenative, or what we think of as more clear, versus neural, more casual speech. And this suggests that the more naturalistic neural TTS may be less intelligible. And we found that this TTS effect was not modulated by signal to noise ratio or semantic predictability in line with prior work. Both of these factors had their own separate effects on intelligibility, and those 2 effects were additive. So it was even lower at a low signal to noise ratio and low predictability, but this really didn't impact TTS type. We also saw differences in the ratings for neural versus concatenative, with higher ratings for human likeness, naturalness, likability, and familiarity for neural versus concatenative speech, in line with recent results for neural TTS, for example, for the WaveNet voices. And furthermore, we found a link between intelligibility and two ratings. So, how natural or human like a particular listener found a voice was directly related to how well they were able to perceive neural TTS in that speech and noise perception task. And this suggests that there's patterns of individual variation, as well as a link between attitudes and intelligibility, as has been seen in human human interaction. So, whether there's also a top down effect here really remains an open question. One possible explanation is that a listener who rated the voice as sounding less human like might have also assumed they would not be able to understand the TTS as well. Again, in line with work by Babel and Russell showing stereotyping, where listeners show reduced accuracy in speech and noise perception based on these top down expectations. So, future work varying voice qualities across different listening conditions, as well as measuring individual differences, for example, computer personification, can really tease apart this possible contribution. So, there are many limitations which can serve as directions for future research that we're excited to explore. For one, doing acoustic phonetic measurements of co-articulation and connected speech would give us more insight whether we see this decrease in neural TTS due to co-articulation, or that maybe those segments weren't as co-articulated as we had hypothesized. We only used one type of background noise here, speech shape noise. In the future, we could use different types of background noise, such as multi-talk or babble. Here we used 4 female talkers, but of course, to generalize this more broadly, you'd want to use other talkers, male talkers, as well as different language backgrounds. And finally, looking at other sources of individual variation, not just the rating of a given voice, but aspects like cognitive processing style measured by AQ could also reveal the relationship between top-down expectations, listener variation, and then that link between the rating and accuracy. This work also has design implications for voice user interface, or VUI. So more naturalistic TTS may not be as intelligible a noise, but you could have a user choose a voice that might sound the most natural or human-like to them. Finally, in considering what acoustic phonetic features could be enhanced in those neural TTS voices, if, for example, the speaker detected background noise to compensate for that deleterious effect on intelligibility. So overall, we see differences in TTS synthesis have an impact on speech and noise perception, even for the identical speaker data set. And additionally, we see the patterns of individual variation in attitudes, how those individuals rate those voices also shape this relationship, but many other questions remain. So thank you to our funding sources, to Yulan Liu and Roland Mass for their feedback on the paper. And that's all. Thanks for coming to the talk.